Right now, as you read these words, you are surrounded by invisible matter that outweighs everything you can see by more than 5 to 1. This dark matter flows through your body at incredible speeds, passes through walls like they don't exist, and shapes the cosmic architecture of the entire universe. Yet we have absolutely no idea what it is made of. Dark matter represents the most profound mystery in modern science, revealing that 85% of all matter exists in a form so alien to our experience that it might as well be made of pure mystery itself. The shocking truth is that the atoms composing your body, every star in the sky, every planet and galaxy we can observe, all the ordinary matter in the universe accounts for less than 5% of cosmic reality. The remaining 95% consists of dark matter and dark energy, substances so strange they interact with ordinary matter almost exclusively through gravity. We live in a universe where we can see only the cosmic equivalent of foam on an ocean whose depths remain completely hidden from us. Dark matter isn't just missing mass that astronomers miscalculated. It is a fundamental component of reality that operates according to rules we do and understand, made of particles we've never detected following physics that might require completely new theories to explain. The mystery goes deeper than simply not knowing what dark matter is made of. Rediscovering the dark matter might force us to reconceptualize what matter itself means in a universe far stranger than we ever imagined. The evidence for dark matter comes from observations spanning cosmic scales from individual galaxies to the largest structures in the universe. Galaxy rotation curves show that stars orbit galactic centers far too quickly to be held in place by visible matter alone. Gravitational lensing reveals invisible mass-bending spacetime around galaxy clusters. The cosmic microwave background preserves fingerprints of dark matter's influence on cosmic evolution when the universe was only 380,000 years old. But perhaps the most compelling evidence comes from the Bullet Cluster, two galaxy clusters that collided billions of years ago, separating ordinary matter from dark matter through cosmic violence and providing direct observational proof that dark matter exists as something distinct from ordinary atoms. This cosmic collision created a natural experiment that revealed dark matter's ghostly properties while confirming that something invisible dominates cosmic mass. The leading candidates for dark matter particles read like a science fiction inventory of exotic physics, weakly interacting massive particles that barely touch ordinary matter, axions so light they make neutrinos seem heavy, sterile neutrinos that interact only through gravity, and primordial black holes left over from the universe's first moments. Each possibility requires different physics, different detection methods, and different implications for our understanding of cosmic reality. Underground laboratories, buried miles beneath Earth's surface, conduct some of the most sensitive experiments ever attempted, trying to catch individual dark matter particles as they pass through detectors cooled to near absolute zero. Space-based observatories search for gamma rays produced when dark matter particles annihilate each other. Particle accelerators attempt to create dark matter in collisions that recreate conditions from the first moments after the Big Bang. Yet, despite decades of increasingly sophisticated searches, dark matter remains invisible, not just to ordinary light, but to every detection method we've devised. This failure to find dark matter has led some scientists to propose that the phenomenon we attribute to dark matter might actually result from modifications to gravity itself, suggesting that Einstein's general relativity breaks down cosmic scales and requires fundamental revision. The implications extend far beyond astronomy into quantum mechanics, particle physics, and cosmology. If dark matter consists of undiscovered particles, it proves that the standard model of particle physics, our most successful theory about fundamental reality, is incomplete. If dark matter requires modified gravity, it suggests that our understanding of space-time itself needs revolutionary updates. But the mystery goes even deeper because dark matter appears to be essential for cosmic evolution. Computer simulations show that without dark matter's gravitational scaffolding, galaxies couldn't form, stars wouldn't ignite, and planets wouldn't exist. Dark matter seems to be the architect of cosmic structure, the invisible foundation that makes visible reality possible. Some theoretical physicists propose that dark matter might represent our first evidence for extra dimensions, supersymmetry, or quantum field effects that operate beyond current understanding. Others suggest dark matter could be composed of entirely different types of matter that follow alternative physics, creating hidden sectors of reality that rarely interact with our familiar world. The search for dark matter has become one of the most expensive and technically challenging endeavors in science, involving underground laboratories, space telescopes, particle accelerators, and supercomputer simulations that collectively represent billions of dollars in research investment. The stakes couldn't be higher because understanding dark matter might revolutionize physics as fundamentally as quantum mechanics and relativity did in the 20th century. If you're ready to explore the universe's greatest mystery and discover what current science tells us about the invisible reality that dominates cosmic existence, subscribe and hit thumbs up. And here is a mind-bending question that challenges everything we think we know about matter. If 85% of cosmic reality consists of particles we've never detected using physics, we do not understand what does. This tell us about the fundamental nature of existence itself? Comment below with your thoughts on whether dark matter represents missing particles or missing understanding. The journey we're about to take will reveal how modern astronomy discovered that most of the universe is invisible while deleting. Particle candidates require physics beyond the standard model, how underground experiments attempt to catch particles that barely exist, and what dark matter's mysterious nature reveals about the deepest structure of physical reality. We'll explore the possibility that dark matter consists of weakly interacting massive particles left over from the Big Bang, examine exotic alternatives like axions that solve multiple physics problems, simultaneously investigate whether modified gravity might eliminate the need for dark matter entirely, and discover how dark matter shapes cosmic evolution from the largest scales to the formation of galaxies and stars. By the end of this exploration, you'll understand that the question, "What is dark matter made of?" represents far more than astronomical curiosity. It's a probe into the fundamental nature of reality that challenges our most basic assumptions about matter, space, time, and the universe's underlying structure. Dark matter might be the key to understanding cosmic reality at its deepest level, or it might represent an entirely new category of existence that transcends current scientific understanding. The answer to what dark matter is made of could revolutionize physics, or it could reveal that we've been asking the wrong question about a universe far stranger and more mysterious than human imagination has yet grasped. Let's begin our investigation into the cosmic mystery that dominates reality while remaining completely invisible to every sense and every instrument we've created to explore the nature of existence itself. Chapter 1. Invisible Universe. The shocking discovery that most of the universe is invisible began with what seemed like a simple astronomical observation in the 1930s, but it has evolved into the most profound mystery in modern science, revealing that our familiar world of atoms, stars, and galaxies represents only a tiny fraction of cosmic reality. This invisible universe that surrounds and permeates everything we can see operates according to rules so alien that it challenges our most fundamental assumptions about the nature of matter and existence itself. Dr. Fritz Zwicky made the first indirect detection of dark matter in 1933 while studying the Coma Galaxy cluster through telescopes at the California Institute of Technology. Zwicky was measuring the velocities of individual galaxies within the cluster when he noticed something impossible. The galaxies were moving far too fast to be gravitationally bound by the visible matter he could observe through his instruments. Using the virial theorem, which relates the kinetic energy of objects in a gravitationally bound system to their potential energy, Zwicky calculated that the Coma cluster contained approximately 400 times more mass than could be accounted for by the luminous matter visible in telescopes. This missing mass problem suggested either that astronomical distance measurements were catastrophically wrong, or that most matter in the universe is completely invisible. Zwicky coined the term dunkle Materie, dark matter in German, to describe this invisible component that seemed to dominate the gravitational behavior of galaxy clusters while remaining undetectable to electromagnetic observations. His calculations suggested that the universe contains vast amounts of matter that emits no light, reflects no radiation, and reveals itself only through gravitational effects on visible matter. The astronomical community largely ignored Zwicky's findings for decades, dismissing them as observational errors or misunderstandings about galaxy cluster dynamics. The idea that most cosmic matter could be invisible seemed too radical to accept, especially when astronomical observations were limited to optical telescopes that could only detect light-emitting objects like stars and glowing gas clouds. But the missing mass problem wouldn't disappear. Radio astronomy observations in the 1960s and 1970s revealed that galaxies contain far more hydrogen gas than optical observations had detected, suggesting that substantial amounts of ordinary matter might exist in forms invisible to optical telescopes. However, even accounting for all possible ordinary matter, including gas, dust, and dead stars, astronomers couldn't explain the gravitational effects Zwicky had discovered. Dr. Vera Rubin's revolutionary work in the 1970s provided the most compelling evidence for dark matter through her studies of galaxy rotation curves. Rubin and her collaborator, Ken Ford, used spectrographic observations to measure how fast stars orbit around galactic centers at different distances, expecting to find that orbital velocities decrease with distance according to Kepler's laws, just as planets orbit more slowly farther from the Sun. Instead, Rubin discovered that stars in the outer regions of galaxies orbit just as fast as stars near galactic centers, creating flat rotation curves that violate Newton's laws of motion and gravitation unless galaxies contain enormous amounts of invisible matter. This dark matter would need to extend far beyond the visible disk of stars, creating massive dark halos that dominate galactic mass and determine orbital dynamics. The implications were staggering. Individual galaxies, not just galaxy clusters, require dark matter to explain their observed behavior. Every spiral galaxy that Rubin studied exhibited flat rotation curves that could only be explained by invisible matter outweighing visible stars and gas by factors of 5 to 10. The universe-to-universe missing mass problem wasn't limited to exotic galaxy clusters. It affected every large gravitational system astronomers could observe. Theoretical astrophysicists like Dr. Jeremiah Ostraker and James Peebles demonstrated through computer simulations that visible galactic disks would be gravitationally unstable without massive dark matter halos to provide additional gravitational support. Their calculations showed that galaxies, as we observe them, simply couldn't exist without dark matter as stabilizing influence on galactic structure and evolution. The Cosmic Background Explorer, COBE, satellite observations in the 1990s reveal additional evidence for dark matter through precise measurements of cosmic microwave background radiation. The tiny temperature fluctuations in this relic radiation from the early universe encode information about cosmic matter, density, and composition when the cosmos was only 380,000 years old. COBE's measurements showed that ordinary atomic matter accounts for only about 4.9% of cosmic density, while dark matter comprises approximately 26.8% of the universe's total matter and energy content. These observations provided independent confirmation of dark matter's existence through completely different physics than galaxy rotation curves or Cluster dynamics. More recent observations by the Wilkinson Microwave Anisotropy Probe, WMP, and Planck satellites have refined these measurements with extraordinary precision, confirming that dark matter outweighs ordinary matter by more than 5 to 1 throughout cosmic history. The cosmic microwave background carries information about dark matter's gravitational effects during cosmic evolution, creating temperature patterns that serve as fossil evidence for dark matter's role in cosmic structure formation. The Wide Field Infrared Survey Explorer, WISE, and other surveys have systematically cataloged the infrared emission from stars, gas, and dust throughout nearby galaxies, enabling precise accounting of all ordinary matter components. These comprehensive surveys confirm that visible matter accounts for only a small fraction of the total mass required to explain observed gravitational effects. Gravitational microlensing surveys, like the Massive Compact Halo Object (MACHO project, have searched for dark matter in the form of massive compact objects like brown dwarfs, black holes, or neutron stars that could provide missing mass without emitting detectable radiation. These surveys have ruled out substantial contributions from most types of compact objects, eliminating ordinary matter candidates for dark matter. Computer simulations of cosmic structure formation, like the Millennium Simulation and Illustris project, demonstrate that observed cosmic structure cannot form without dark matter's gravitational scaffolding. These simulations show how dark matter halos provide frameworks for ordinary matter to collect and form stars, galaxies, and larger cosmic structures over billions of years. The Lambda-Cold Dark Matter (CDM) model has become the standard cosmological framework that incorporates dark matter as an essential component of cosmic evolution. This model successfully predicts the large-scale structure of the universe, galaxy formation rates, and cosmic microwave background patterns, while requiring dark matter to comprise about 85% of all matter in the universe. Recent observations by the Dark Energy Survey and other large-scale structure surveys continue to find evidence for dark matter through weak gravitational lensing effects that reveal how invisible matter distributions affect light from distant galaxies. These observations provide additional confirmation that dark matter exists as something distinct from ordinary atomic matter. The cumulative evidence from galaxy rotation curves, cluster dynamics, cosmic microwave background observations, Big Bang nucleosynthesis, gravitational lensing, and cosmic structure formation creates an overwhelming case for dark matter's existence. Multiple independent observations using completely different physics all point to the same conclusion. Most matter in the universe consists of particles that interact gravitationally but remain invisible to electromagnetic radiation. Yet despite this compelling observational evidence, the fundamental question remains completely unanswered. What is dark matter made of? The invisible universe that dominates cosmic reality continues to hide its composition from every experimental technique designed to reveal the nature of matter at its most fundamental level. We know dark matter exists, we can map its distribution, we can measure its gravitational effects, but we have no idea what it actually is. This profound mystery reveals that our understanding of matter itself might be fundamentally incomplete. The familiar atomic matter described by chemistry and nuclear physics represents only a tiny fraction of cosmic reality, while the dominant component of matter exists in forms that might require entirely new physics to understand. The invisible universe challenges every assumption about the relationship between matter and observation, between existence and detection, between what is real and what is knowable. The discovery of the invisible universe represents one of the most humbling realizations in the history of science. We live in a cosmos dominated by phenomena we cannot see, cannot touch, and cannot directly detect yet, which fundamentally determine the structure and evolution of everything we can observe. Dark matter reveals that cosmic reality extends far beyond human sensory experience into realms that might require revolutionary new concepts to comprehend. Understanding that most of the universe is invisible transforms questions about cosmic composition from astronomical curiosity into fundamental inquiries about the nature of existence itself. The invisible universe that surrounds us represents the cosmic majority, making the visible world we experience a small and perhaps unrepresentative sample of what reality actually contains at its deepest level. Chapter 2. Cosmic Evidence. The evidence for dark matter's existence has accumulated from multiple independent observations, spanning different scales of cosmic structure, creating one of the most robust conclusions in modern astrophysics, despite the fact that dark matter has never been directly detected. This cosmic evidence comes from phenomena as diverse as the rotation of individual galaxies, the collision of galaxy clusters, the formation of cosmic structure, and the relic radiation from the Big Bang itself, all pointing to the same startling conclusion. Most matter in the universe is invisible. Galaxy rotation curves provide the most direct and compelling evidence for dark matter through measurements that reveal how orbital velocities change with distance from galactic centers. Dr. Vera Rubin's pioneering observations showed that stars in spiral galaxies maintain nearly constant orbital velocities, even at large distances from galactic cores, violating Kepler's laws, which predict that orbital speeds should decrease with distance, just as planetary velocities decrease farther from the Sun. The Andromeda Galaxy, our nearest large galactic neighbor, exhibits a rotation curve that remains flat out to distances exceeding 100,000 light-years from its center. If only visible matter determined orbital dynamics, stars at these distances should orbit at velocities around 50 kilometers per second. Instead, they maintain velocities near 250 kilometers per second, requiring approximately 10 times more gravitational mass than visible stars and gas can provide. Modern radio astronomy observations using hydrogen's 21-centimeter emission line enable precise velocity measurements, extending far beyond the visible stellar disk in spiral galaxies. These observations reveal that flat rotation curves persist to the limits of detectable hydrogen gas, suggesting that dark matter halos extend to distances several times larger than visible galactic structure. Elliptical galaxies provide additional rotation curve evidence through measurements of stellar velocity dispersions and planetary nebula motions. Dr. Douglas Richstone's observations of elliptical galaxy kinematics show that these systems also require dark matter halos to explain the observed stellar motions, demonstrating that dark matter is a universal feature of large galaxies, regardless of their morphological type. Galaxy cluster dynamics offer evidence for dark matter on scales much larger than individual galaxies through measurements of galaxy velocities within massive cluster systems. The original Coma cluster observations by Fritz Zwicky have been confirmed and extended by modern surveys that measure velocities for hundreds of galaxies within individual clusters. The Virgo cluster, the nearest large galaxy cluster to our local group, contains more than 2,000 galaxies moving with velocities that require cluster mass approximately 50 times greater than the visible matter content. X-ray observations of hot gas within the cluster provide additional mass estimates that remain insufficient to explain the observed galaxy motions without invoking substantial dark matter components. Gravitational lensing provides perhaps the most direct evidence for dark matter by revealing how invisible mass bends spacetime and deflects light from background objects. Strong gravitational lensing around massive galaxy clusters creates multiple images, arcs, and rings of distant galaxies that can be used to map the total mass distribution, including both visible and dark components. The Hubble Space Telescope has observed hundreds of gravitational lensing systems that reveal dark matter distributions, extending far beyond visible cluster galaxies. These observations show that dark matter forms large-scale structure that often does not correspond exactly to visible matter distributions, providing additional evidence that dark matter exists as something distinct from ordinary atomic matter. Weak gravitational lensing surveys, like the Dark Energy Survey, analyze subtle shape distortions in millions of background galaxies to map dark matter distributions across cosmic scales. These statistical measurements reveal how dark matter forms a cosmic web of filaments and nodes that provides the gravitational framework for visible cosmic structure. The Bullet Cluster provides the most dramatic evidence for dark matter through observations of two galaxy clusters that collided approximately 150 million years ago. During this cosmic collision, the ordinary matter in each cluster interacted through electromagnetic forces and friction, causing hot gas clouds to lag behind the cluster galaxies during the collision. Dr. Doug Cloh's observations of the Bullet Cluster using both optical telescopes and X-ray observations revealed that the total gravitational mass, as measured through gravitational lensing, is displaced from the X-ray emitting gas that traces ordinary matter distributions. This spatial separation between total mass and ordinary matter provides direct evidence that most cluster mass consists of dark matter that passed through the collision without significant interaction. Cosmic microwave background observations provide evidence for dark matter through detailed analysis of temperature fluctuations that encode information about cosmic composition and evolution. The European Space Agency's Planck satellite has measured these fluctuations with extraordinary precision, revealing patterns that can only be explained by specific ratios of ordinary matter, dark matter, and dark energy. The cosmic microwave background power spectrum shows a series of acoustic peaks that result from sound waves propagating through the early universe before atoms formed and space became transparent to radiation. The relative heights and positions of these peaks depend sensitively on cosmic matter density and composition, providing precision measurements of dark matter abundance. Big Bang nucleosynthesis provides independent evidence for dark matter by constraining the density of ordinary atomic matter during the universe's first few minutes. Theoretical calculations of light element production during primordial nucleosynthesis predict specific ratios of hydrogen, helium, and lithium that depend on ordinary matter density, but are independent of dark matter abundance. Observations of primordial light element abundances in old stars and low metallicity gas clouds confirm Big Bang nucleosynthesis predictions while demonstrating that ordinary matter comprises only about 4.9% of cosmic density. Since gravitational observations require total matter density around 31% of critical density, approximately 85% of cosmic matter must be non-atomic dark matter. Large-scale structure formation provides additional evidence for dark matter through observations of galaxy clustering patterns and cosmic web architecture. The 2-degree field galaxy redshift survey and Sloan Digital Sky survey have mapped the three-dimensional distribution of millions of galaxies, revealing large-scale structure that matches computer simulations only when dark matter is included as the dominant matter component. Cosmic structure formation simulations like the Illustris project and Eagle simulations demonstrate that observed galaxy properties, including sizes, masses, star formation rates, and clustering patterns, can only be reproduced when dark matter provides the gravitational scaffolding for ordinary matter to collapse and form stars and galaxies over cosmic time. Type Ia supernova observations provide evidence for cosmic acceleration driven by dark energy, which affects the cosmic matter budget and confirms that matter, both ordinary and dark, comprises only about 31% of total cosmic energy density. These observations support the overall cosmological framework that includes dark matter as an essential component. Cosmic shear surveys measure correlations in galaxy shape, distortions caused by gravitational lensing from intervening dark matter structures. The Kilo-degree survey and Dark Energy survey have detected these correlations across cosmic scales, providing direct measurements of dark matter clustering that agree with theoretical predictions from the standard cosmological model. Satellite galaxy observations around the Milky Way and Andromeda provide evidence for dark matter through studies of dwarf galaxy dynamics and spatial distributions. The Large Magellanic Cloud and other satellite galaxies exhibit internal velocity dispersions that require dark matter halos despite their small visible masses, extending dark matter evidence to the smallest galaxy scales. Galaxy weak lensing measurements detect gravitational effects from dark matter halos around individual galaxies by measuring subtle shape correlations between foreground lens galaxies and background source galaxies. These observations reveal that dark matter halos extend well beyond visible galaxy boundaries and follow predictable scaling relationships with galaxy properties. The evidence for dark matter has accumulated across 5 orders of magnitude in scale, from dwarf galaxies with masses around YY solar masses to galaxy clusters with masses exceeding 1,015 solar masses. This consistency across such diverse systems and physical scales creates one of the most robust conclusions in observational astrophysics, despite the fundamental mystery about dark matter as composition. Modern surveys continue to refine and extend dark matter evidence through increasingly precise observations to test the standard cosmological model while searching for clues about dark matter's nature. The Legacy Survey of Space and Time at the Vera Rubin Observatory will observe billions of galaxies to map dark matter distributions with unprecedented detail and statistical precision. The cosmic evidence for dark matter represents a remarkable convergence of observations from different physical phenomena measurement techniques and cosmic scales that all point to the same conclusion. Most matter in the universe exists in a form completely unlike the atomic matter that comprises stars, planets, and life. This evidence base provides the foundation for efforts to understand what dark matter is made of, even though its composition remains one of the deepest mysteries in science. Chapter 3. Particle Zoo. The quest to understand what dark matter is made of has led theoretical physicists to propose an exotic menagerie of hypothetical particles that could exist in the universe while remaining invisible to ordinary matter. This particle zoo of dark matter candidates represents some of the most creative and sophisticated thinking in modern physics, extending our understanding of matter far beyond the familiar particles described by the standard model, while opening windows into entirely new realms of physical reality. The most widely studied dark matter candidates are weakly interacting massive particles, or WIMPs, which provide elegant solutions to multiple cosmological problems while emerging naturally from extensions to the standard model of particle physics. WIMPs interact with ordinary matter only through gravity and the weak nuclear force, making them nearly impossible to detect while allowing them to survive from the early universe to the present day in the quantities required to explain dark matter observations. Supersymmetric particles represent the leading class of WIMP candidates, emerging from supersymmetry theories that predict a shadow particle for every known particle in the standard model. The lightest supersymmetric particle, often called the neutralino, would be stable due to conservation laws and could have precisely the properties needed to serve as dark matter while solving other problems in particle physics like the hierarchy problem and gauge coupling unification. Dr. Howard Baer and other supersymmetry theorists have calculated that neutralinos produced during Big Bang nucleosynthesis would naturally result in the observed dark matter abundance if they have masses between 100 and 1,000 times the proton mass. These calculations provide a compelling WIMP miracle. The remarkable coincidence that particles with weak interaction cross-sections naturally produce the correct dark matter abundance through thermal equilibrium processes in the early universe. Axions represent another leading dark matter candidate with completely different properties than WIMPs. Emerging from solutions to the strong CP problem in quantum chromodynamics, proposed by Roberto Piquet and Helen Quinn in 1977, axions would be extraordinarily light particles, with masses millions or billions of times smaller than electrons, that interact with ordinary matter primarily through interactions with electromagnetic fields. The axion was named by Frank Wilczek after a laundry detergent brand because it cleans up the strong CP problem by introducing a dynamic field that adjusts to eliminate charge parity violation in strong nuclear interactions. This theoretical motivation for axions is completely independent of dark matter considerations, making axions attractive candidates that could solve multiple physics problems simultaneously. Primordial black holes offer a radically different approach to dark matter that doesn't require new particle physics, instead proposing that dark matter consists of black holes formed during the early universe from primordial density fluctuations. Dr. Stephen Hawking and Bernard Carr showed that black holes with masses between 10 to 8 and 100 solar masses could serve as dark matter while avoiding conflicts with Big Bang nucleosynthesis and other observational constraints. Recent theoretical work by Dr. Juan Garcia Bellido and others suggests that primordial black holes could form from cosmic inflation if inflation produced large density fluctuations on small scales. Advanced LIGO's gravitational wave detections of black hole mergers have renewed interest in primordial black hole dark matter, though observational constraints limit their possible contribution to total dark matter abundance. Sterile neutrinos represent another exotic dark matter possibility involving particles that interact only through gravity, making them even more elusive than ordinary neutrinos that interact through the weak nuclear force. Dr. Alexander Kusenko and others have proposed that sterile neutrinos with masses between 1 and 100 keV could serve as warm dark matter that would modify cosmic structure formation on small scales compared to cold dark matter scenarios. Dark photons and hidden sector particles propose that dark matter might consist of particles that interact through completely separate forces from those affecting ordinary matter. These dark sector theories suggest that dark matter particles might experience dark electromagnetic forces, dark strong forces, and complex dark chemistry that creates rich hidden physics operating parallel to ordinary matter interactions. Self-interacting dark matter models propose that dark matter particles interact strongly with each other while remaining invisible to ordinary matter. Dr. David Spergel and Paul Steinhardt showed that dark matter self-interactions could solve several problems with standard cold dark matter models, including the diversity of dwarf galaxy density profiles and the missing satellite problem around large galaxies. Fuzzy dark matter or ultralight scalar field dark matter consists of extremely light particles with masses around Y-22 electron volts that behave as quantum waves rather than classical particles on galactic scales. Dr. Lam Hui and others have shown that these quantum interference effects could suppress small-scale structure formation while producing distinctive signatures in dwarf galaxy properties and galactic center dynamics. Q-balls and other non-topological solitons represent exotic dark matter candidates consisting of coherent field configurations that maintain stability through quantum effects rather than topological protection. These extended objects could have masses ranging from elementary particles to macroscopic scales while remaining difficult to detect through conventional means. Mirror matter theories propose that dark matter consists of mirror particles that experience mirror electromagnetic, weak and strong forces, but interact with ordinary matter only through gravity and potentially very weak mixing interactions. This approach could explain dark matter while preserving familiar physics in a hidden mirror sector of reality. Toulouse-Klein particles emerge from extra-dimensional theories where dark matter consists of ordinary particles, propagating through additional spatial dimensions beyond our familiar three. These particles would appear as invisible matter in our three-dimensional slice of higher-dimensional space-time while following familiar physics rules in the full-dimensional space. Asymmetric dark matter models propose that dark matter abundance results from matter-antimatter asymmetry, similar to the process that created ordinary matter abundance in the early universe. Dr. Catherine Zurich and others have developed scenarios where dark matter and ordinary matter abundances are related through common mechanisms that produce both dark and visible matter asymmetries. Strongly interacting massive particles, SIMPs, represent dark matter candidates that interact strongly with each other through dark force carriers while remaining invisible to ordinary matter. These models can produce the correct dark matter abundance through processes involving dark matter self-annihilation rather than interactions with ordinary matter. Superfluid dark matter proposes that dark matter behaves as a quantum superfluid on galactic scales, creating phenomena like quantized vortices and collective modes that could explain galactic rotation curves without invoking particle dark matter. Dr. Justin Cowrie and others have developed models where dark matter superfluidity emerges at low temperatures and densities characteristic of galaxy halos. Dark matter bound states and dark atoms suggest that dark matter might form complex structures through dark electromagnetic forces, creating dark molecules, dark chemistry, and dark condensed matter physics that operates in parallel to ordinary atomic physics. These models could explain dark matter's observed properties while predicting rich hidden sector phenomenology. Composite dark matter theories propose that dark matter consists of bound states of more fundamental dark particles, analogous to how protons and neutrons are composite particles made of quarks. These scenarios could explain dark matter stability through confinement mechanisms, similar to quantum chromodynamics, while predicting complex dark matter spectroscopy. The diversity of dark matter candidates reflects both the flexibility of theoretical physics and the limited observational constraints on dark matter properties. Current observations tell us that dark matter is cold, non-relativistic, stable on cosmic timescales, and interacts weakly with ordinary matter and electromagnetic radiation. But these constraints still permit enormous variety in possible particle properties and interactions. Each dark matter candidate makes specific predictions for detection experiments, cosmic structure formation, and particle physics signatures that could distinguish between different possibilities. The challenge for experimental physics is developing detection techniques sensitive enough to test these theoretical predictions while covering the enormous range of possible dark matter masses, interaction strengths, and production mechanisms. The particle zoo of dark matter candidates demonstrates the creativity and sophistication of modern theoretical physics, while revealing how much we still do understand about the fundamental nature of matter. These exotic possibilities extend our conception of what matter can be far beyond everyday experience, suggesting that cosmic reality might be far richer and more complex than the visible world suggests. Understanding the full range of dark matter candidates reveals why discovering dark matter's composition would revolutionize physics by either confirming extensions to the standard model, revealing new fundamental forces and interactions, or demonstrating that matter can exist in forms completely unlike anything we've previously encountered. The particle zoo represents our best attempts to imagine what invisible cosmic reality might contain. Chapter 4. WIMPs and Shadows Weakly Interacting Massive Particles, or WIMPs, represent the most extensively studied and theoretically motivated candidates for dark matter, emerging naturally from extensions to the standard model of particle physics while providing elegant explanations for dark matter's observed properties. WIMPs embody what physicists call the RIMP miracle, the remarkable fact that particles interacting through weak nuclear forces would naturally produce the correct dark matter abundance in the early universe, making them prime suspects for solving the cosmic dark matter mystery. The theoretical foundation for WIMPs emerges from supersymmetry, one of the most promising extensions to the Standard Model that predicts a superpartner particle for every known particle. In supersymmetric theories, every fermion has a bosonic superpartner, and every boson has a fermionic superpartner, effectively doubling the particle content of the Standard Model, while solving several fundamental problems in particle physics, including the hierarchy problem and gauge coupling unification. The lightest supersymmetric particle, often called the neutralino, emerges as a natural dark matter candidate because R-parity conservation in most supersymmetric models makes it absolutely stable. It cannot decay into Standard Model particles. Dr. Howard Baer and other supersymmetry theorists have shown that neutralinos with masses between 100 and 1000 GeV would have precisely the interaction strengths needed to explain observed dark matter abundance. The WIMP miracle occurs because particles that interact through weak nuclear forces naturally freeze out of thermal equilibrium in the early universe when their interaction rate drops below the cosmic expansion rate. This freeze-out mechanism produces particle abundances that depend on interaction cross-sections in exactly the right way to explain dark matter observations if the particles have weak-scale masses and interaction strengths. Dr. Gerard Jungmann, Mark Kamionkovsky, and Kim Griest's comprehensive analysis of WIMP cosmology demonstrated that thermal relic abundances for weak-scale particles automatically yield cosmic densities matching dark matter observations. This coincidence between particle physics scales and cosmological requirements provides compelling motivation for WIMP dark matter scenarios. Neutralinos represent the most studied WIMP candidate, consisting of quantum superpositions of supersymmetric partners of neutral gauge bosons and Higgs particles. The neutralino's properties depend on supersymmetry breaking patterns and mixing parameters that determine its mass, composition, and interaction strengths with Standard Model particles through G boson, Higgs boson, and squark exchange processes. Different supersymmetric models predict neutralinos with varying properties that affect both their cosmic abundance and their detectability in laboratory experiments. Minimal supergravity models, gauge-mediated supersymmetry breaking scenarios, and anomaly-mediated supersymmetry breaking frameworks each predict different neutralino masses and interaction patterns that lead to distinct experimental signatures. Direct detection of WIMPs relies on measuring nuclear recoils produced when dark matter particles scatter elastically off atomic nuclei in underground detectors. The interaction rate depends on the WIMP nucleon scattering cross-section, local dark matter density, and WIMP velocity distribution, with event rates typically predicted to be less than 1 interaction per kilogram of target material per day. Spin-independent WIMP interactions occur through scalar coupling to nucleons and scale with the square of nuclear mass, making heavy nuclei like xenon and germanium optimal targets for detection. Spin-dependent interactions involve axial vector coupling to unpaired nucleon spins and are most effective with light nuclei containing unpaired protons or neutrons. The cryogenic dark matter search, CDMs, and Edelweiss collaborations pioneered cryogenic detector technology that simultaneously measures phonon and ionization signals from particle interactions, enabling discrimination between nuclear recoils from dark matter and electron recoils from background radiation through different signal ratios. Liquid xenon detectors like Xenon and Lux collaborations use dual-phase technology that measures both scintillation light and ionization electrons from particle interactions in liquid xenon, providing excellent background discrimination and scalability to larger target masses. These experiments have achieved sensitivities approaching Y-47 square centimeters, FOR WIMP nucleon scattering cross-sections. Argon-based detectors like dark-side and DPL aberrations exploit pulse-shape discrimination in liquid argon to distinguish nuclear recoils from electromagnetic backgrounds. While argon's lower mass compared to xenon provides enhanced sensitivity to lower mass WIMPs through improved kinematic matching. Directional detection experiments like drift and newage attempt to measure the direction of nuclear recoils produced by WIMP interactions, exploiting the fact that Earth's motion through the galactic dark matter halo should create a preferred direction for WIMP-induced nuclear recoils that changes with Earth's rotation and orbital motion. Indirect detection of WIMPs focuses on searching for annihilation products when dark matter particles encounter their antiparticles in regions of high dark matter density. WIMP annihilation could produce gamma rays, neutrinos, antimatter, or other detectable particles that would provide signatures of dark matter interactions in cosmic ray observations. The Fermi Large Area Telescope searches for gamma ray excess emission from dwarf spheroidal galaxies, galaxy clusters, and the galactic center that could result from WIMP annihilation. These searches constrain WIMP annihilation cross-sections while searching for spectral features that would indicate specific dark matter particle masses and annihilation channels. IceCube and other neutrino telescopes search for high-energy neutrinos produced by WIMP annihilation in the Sun's core, where dark matter particles could accumulate through gravitational capture and elastic scattering with solar nuclei. Solar WIMP searches provide complementary constraints to direct detection experiments while probing spin-dependent WIMP interactions. Antimatter searches using the Alpha Magnetic Spectrometer on the International Space Station and balloon-borne experiments look for excess positrons, antiprotons, or antideuterons that could result from WIMP annihilation processes. These searches must distinguish dark matter signals from astrophysical sources like pulsar wind interactions and cosmic ray spallation. Collider searches at the Large Hadron Collider attempt to produce dark matter particles directly in high-energy proton-proton collisions, detecting them through missing energy signatures when WIMPs escape the detector without interacting. These searches probe WIMP production mechanisms while constraining models that connect dark matter to electroweak symmetry breaking. Despite decades of increasingly sensitive searches, no experiment has conclusively detected WIMP dark matter, creating tension between theoretical expectations and observational limits. Current constraints exclude large regions of WIMP parameter space, including much of the parameter space predicted by simple supersymmetric models that motivated WIMP searches. The WIMP crisis has emerged as direct detection experiments approach the neutrino background limit without finding dark matter signals, while indirect searches constrain WIMP annihilation cross-sections to values below thermal relic predictions for many models. This crisis has motivated exploration of alternative dark matter candidates and modified WIMP scenarios. However, substantial viable parameter space remains for WIMP dark matter, particularly for scenarios involving non-standard cosmological histories, co-annihilation processes, resonant annihilation mechanisms, or WIMPs with masses outside the traditional weak-scale range. These possibilities could explain dark matter while evading current experimental constraints. Next-generation experiments like XENONNT, LUX-ZEPPELIN, and Darwin will probe WIMP parameter space with sensitivities approaching the neutrino background limit, providing definitive tests of traditional WIMP scenarios while searching for more subtle signatures that might indicate dark matter interactions. The shadow world of supersymmetric particles represents one of physics' most ambitious theoretical constructions, predicting entire hidden sectors of reality that interact weakly with ordinary matter while solving fundamental problems in particle physics and cosmology. Whether WIMPs exist or not, The search for them has driven extraordinary advances in detector technology, underground laboratory techniques, and precision measurement capabilities. Understanding WIMPs and their properties reveals both the power and limitations of theoretical physics in predicting phenomena beyond current observation. The WIMP paradigm demonstrates how particle physics and cosmology can constrain each other, while showing how experimental searches can test theoretical ideas about the fundamental nature of matter and cosmic evolution. The shadow world of WIMPs, whether it exists or not, has transformed our understanding of what matter might be and how invisible particles could dominate cosmic evolution while remaining almost completely decoupled from ordinary atomic matter. WIMPs represent our most detailed attempt to imagine what dark matter particles could be like, while respecting both particle physics, principles, and cosmological observations. Chapter 5. Exotic Alternatives. Beyond the familiar territory of WIMPs lies a vast landscape of exotic dark matter candidates that push the boundaries of theoretical physics into realms where particles behave more like waves, where quantum fields acquire cosmic significance, and where the distinction between matter and energy becomes blurred. These exotic alternatives represent some of the most creative thinking in modern physics, proposing dark matter solutions that challenge our fundamental concepts about what matter can be. Axions represent perhaps the most elegant exotic dark matter candidate, emerging not from cosmological needs, but from solutions to a fundamental problem in quantum chromodynamics called the strong CP problem. The axion was proposed by Roberto Paquet and Helen Quinn in 1977 as a consequence of a new symmetry that would naturally explain why the strong nuclear force doesn't violate charge parity symmetry, despite theoretical expectations that it should. The axion field permeates all of space as a dynamic quantum field that adjusts its value to minimize violations of CP symmetry in strong interactions. This adjustment mechanism requires the axion to be an extraordinarily light particle, with mass potentially billions of times smaller than the electron mass, making axions behave more like classical fields than individual particles on astronomical scales. Frank Wilczek named the axion after a laundry detergent brand because it cleans up the strong CP problem. But this theoretical motivation, independent of dark matter considerations, makes axions particularly attractive. They could solve two fundamental physics problems simultaneously while emerging from well-motivated extensions to quantum field theory. Axion dark matter would have formed through several mechanisms in the early universe, including vacuum realignment, decay of cosmic strings, and thermal production in primordial plasma. The vacuum realignment mechanism is particularly interesting because it doesn't require thermal equilibrium, allowing axions to be produced even if they never interact strongly with ordinary matter or radiation. Pierre-Saikivi's theoretical work demonstrated that axions would interact with electromagnetic fields through a coupling that depends on axion mass and field strength. This interaction enables experimental searches using microwave cavities in strong magnetic fields, where axion-photon conversion could produce detectable electromagnetic signals with frequencies determined by axion masses. The axion dark matter experiment, a DMX, uses superconducting microwave cavities in strong magnetic fields to search for axion-photon conversion, achieving sensitivity levels that probe cosmologically relevant axion parameter space. ADMX and similar experiments like Haystack and Oregon search for extremely weak electromagnetic signals that would indicate axion dark matter interactions. Fuzzy dark matter or ultralight dark matter proposes that dark matter consists of scalar field particles with masses around 10 to 22 electron volts, making them so light that quantum uncertainty relations create wavelengths comparable to galaxy sizes. Dr. Wayne, Wu and others showed that these quantum effects would suppress small-scale structure formation while producing distinctive oscillations in dark matter density profiles. The quantum nature of ultralight dark matter means that individual particles behave as matter waves with de Broglie wavelengths spanning kiloparsecs, creating quantum interference effects on galactic scales that have no analog in classical particle dark matter. These interference patterns could explain observed features in dwarf galaxy rotation curves and galactic center dynamics that are difficult to understand with conventional dark matter. Lam Hui's analysis of fuzzy dark matter demonstrated that quantum pressure from uncertainty relations would prevent dark matter from forming structures below the quantum coherence scale, naturally explaining why observed satellite galaxies around the Milky Way are less numerous and more diffuse than predicted by standard cold dark matter simulations. Sterile neutrinos represent another exotic dark matter possibility involving particles that interact only through gravity, making them even more elusive than ordinary neutrinos that participate in weak nuclear interactions. These hypothetical particles could have masses ranging from keV to GeV scales while remaining stable on cosmic timescales. Warm dark matter scenarios involving keV-scale sterile neutrinos would be relativistic during cosmic structure formation, creating top-down structure formation patterns that differ from cold dark matter predictions. Dr. Alexander Kusenko and others have shown that sterile neutrino production through oscillations with ordinary neutrinos could generate the correct dark matter abundance while producing distinctive signatures in cosmic structure formation. X-ray astronomy searches for sterile neutrino dark matter focus on detecting photons produced when sterile neutrinos decay through mixing with ordinary neutrinos. Several claimed detections of unidentified X-ray lines in galaxy clusters and dwarf galaxies have been interpreted as possible sterile neutrino decay signals, though these interpretations remain controversial. Self-interacting dark matter proposes that dark matter particles experience strong interactions with each other while remaining invisible to ordinary matter. David Spergel and Paul Steinhardt showed that dark matter self-interactions could solve several problems with standard cold dark matter models, including the diversity problem in dwarf galaxy density profiles and the Corcus problem in galaxy centers. Dark matter self-interactions would transfer energy and momentum between dark matter particles through elastic scattering, creating thermalization effects that could flatten dark matter density profiles in galaxy centers while preserving dark matter's ability to form large-scale structure. The interaction strength must be carefully tuned to affect small galactic scales while not disrupting cluster dynamics. Hidden sector dark matter models propose entire hidden worlds of particles that interact through dark electromagnetic forces, dark weak forces, and dark strong forces completely analogous to ordinary matter interactions. These scenarios could produce dark atoms, dark molecules, dark chemistry, and dark condensed matter physics operating in parallel to ordinary matter. Dr. Reuven Essig and others have developed models where dark matter consists of dark electrons bound to dark nuclei through dark photon interactions, creating dark atomic matter that could exhibit rich phenomenology, including dark plasma physics, dark stellar evolution, and dark planet formation in cosmic regions with high dark matter density. Mirror matter theories propose that dark matter consists of mirror particles experiencing mirror copies of all standard model forces and interactions. This approach preserves familiar physics while explaining dark matter through particles that are identical to ordinary particles except for living in a mirror sector that communicates with ordinary matter only through gravity. Primordial black holes offer a radically different approach, where dark matter consists of black holes formed during the early universe rather than fundamental particles. These black holes could form from large density fluctuations during cosmic inflation, creating a spectrum of black hole masses that could explain all or part of dark matter while avoiding conflicts with Big Bang nucleosynthesis. Recent gravitational wave detections by LIGO have renewed interest in primordial black hole dark matter because the observed black hole masses lie in ranges that could avoid most observational constraints on primordial black holes. However, detailed analysis of gravitational lensing, cosmic microwave background, and other observations severely constrains primordial black hole contributions to dark matter. Cuballs and other non-topological solitons represent exotic dark matter candidates consisting of stable field configurations that maintain coherence through quantum effects rather than topological protection. These extended objects could range from elementary particle scales to macroscopic sizes, while carrying conserved quantum numbers that ensure stability. Superfluid dark matter proposes that dark matter behaves as a quantum superfluid on galactic scales, exhibiting phenomena like quantized vortices and collective excitations that could modify galactic dynamics in ways that mimic dark matter effects without requiring particle dark matter. Dr. Justin Cowrie has shown that superfluid phonons could contribute to galactic rotation curves. Dark photon dark matter involves vector boson particles that couple weakly to ordinary photons through kinetic mixing, creating hidden electromagnetic interactions that could be probed through precision tests of electromagnetic theory. Dark photons could constitute all of dark matter if they acquire masses through hidden sector Higgs mechanisms. The zoo of exotic dark matter alternatives demonstrates both the creativity of theoretical physics and the limited constraints that current observations place on dark matter properties. Each possibility makes specific predictions for astronomical observations, laboratory experiments, and cosmic structure formation that could potentially distinguish between different scenarios. Advanced detector concepts are being developed to search for these exotic alternatives, including quantum sensors for ultralight dark matter, precision atomic clocks for dark photon interactions, and novel techniques for detecting macroscopic dark matter candidates. The diversity of possible detection methods reflects the enormous range of conceivable dark matter properties. The exotic landscape of dark matter alternatives reveals how much we still do not understand about the fundamental nature of matter and cosmic evolution. These possibilities extend our conception of what matter can be far beyond everyday experience, while suggesting that cosmic reality might contain forms of existence completely unlike anything we've encountered in terrestrial physics. Understanding exotic dark matter alternatives illuminates both the sophistication of modern theoretical physics and the profound mystery that dark matter represents for our understanding of cosmic reality. Whether any of these alternatives corresponds to actual dark matter remains unknown, but exploring them expands our imagination about what invisible cosmic reality might contain. Chapter 6. Detection Dreams. The quest to detect dark matter represents one of the most technically challenging and intellectually ambitious endeavors in modern science, pushing experimental physics to its absolute limits while requiring innovations in detector technology, underground laboratory construction, and signal processing that exceed anything previously attempted. These detection efforts span multiple experimental approaches, from deep underground laboratories to space-based observatories to particle accelerators, each designed to catch glimpses of invisible particles that might interact with ordinary matter only once in a billion years. Underground direct detection experiments represent the most straightforward approach to dark matter discovery, designed to measure the tiny energy deposits that would result when dark matter particles collide with atomic nuclei in carefully shielded detectors. These experiments must achieve sensitivities capable of detecting nuclear recoils with energies as low as a few keV, while discriminating against backgrounds from cosmic rays, radioactivity, and environmental contamination. The challenge of direct detection begins with the expected interaction rates, which are extraordinarily small, even for optimistic dark matter scenarios. A typical WIMP with standard interaction strength might produce only 1 detectable collision per 100 kilograms of target material per year, requiring detector systems that can operate continuously for years while maintaining perfect calibration and background control. Dr. Elena Aprol's xenon collaboration has developed liquid xenon detectors that simultaneously measure scintillation light and ionization, electrons produced by particle interactions, enabling discrimination between nuclear recoils from dark matter and electron recoils from background radiation. The latest xenon NT detector contains 8.3 tons of liquid xenon and has achieved background rates as low as 1 event per ton per year. Cryogenic detectors pioneered by the Cryogenic Dark Matter Search (CDMS) and Edelweiss collaborations operate at temperatures near absolute zero to measure both phonon and ionization signals from particle interactions. These detectors exploit the different ratios of phonon to ionization production for nuclear recoils versus electron recoils to identify potential dark matter events. The challenge of background discrimination requires understanding every possible source of signals that could mimic dark matter interactions. Cosmic ray muons can penetrate deep underground and produce neutrons through nuclear interactions in surrounding rock. Radioactive contamination from uranium and thorium decay chains can produce alpha particles and gamma rays that interact with detector materials. Advanced background rejection techniques include active veto systems that surround primary detectors with additional detector layers to identify cosmic ray muons and neutrons. Pulse shape analysis exploits differences in the temporal evolution of signals from different types of particle interactions. Multiple detector technologies can be combined to cross-check potential dark matter signals. Underground laboratory locations are essential for direct detection because cosmic ray shielding improves dramatically with depth. The SURF Laboratory in South Dakota provides 4,200 meters of water-equivalent shielding. The Gran Sasso Laboratory in Italy offers 3,800 meters of rock shielding. These depths reduce cosmic ray muon flux by factors of millions compared to surface levels. Liquid noble gas detectors have emerged as leading direct detection technologies because xenon and argon provide excellent scintillation and ionization properties while being scalable to large target masses. The Lux Zeppelin LZ experiment will deploy 10 tons of liquid xenon in the SURF underground laboratory, representing the current generation of dark matter detectors. Directional detection represents a revolutionary approach that attempts to measure not just the energy, but also the direction of nuclear recoils produced by dark matter interactions. Earth's motion through the galactic dark matter halo should create a preferred direction for dark matter-induced recoils that changes predictably with Earth's rotation and orbital motion. The DRIFT collaboration uses low-pressure gas detectors with optical readout to track the paths of recoiling nuclei, potentially enabling detection of the directional signature that would provide definitive proof of dark matter interactions. Directional detection could distinguish dark matter signals from backgrounds, even with very few events. Indirect detection experiments search for the products of dark matter annihilation or decay in regions where dark matter density is highest, such as galaxy centers, dwarf galaxies, and galaxy clusters. When dark matter particles encounter their antiparticles, they annihilate and produce standard model particles, including photons, neutrinos, and antimatter that could be detected by conventional astronomical instruments. Gamma-ray astronomy provides powerful tools for indirect dark matter searches because many dark matter candidates would produce high-energy photons, either directly through annihilation or indirectly through the decay of unstable particles produced in annihilation processes. The Fermi Large Area Telescope has conducted comprehensive surveys searching for dark matter annihilation signatures. Dwarf spheroidal galaxies represent optimal targets for indirect detection because they contain large amounts of dark matter with minimal astrophysical backgrounds from star formation or active galactic nuclei. The Fermi collaboration has analyzed gamma-ray observations from more than 40 dwarf galaxies to constrain dark matter annihilation cross-sections. Neutrino telescopes like IceCube search for high-energy neutrinos produced by dark matter annihilation in the Sun's core, where dark matter particles could accumulate through gravitational capture and elastic scattering with solar nuclei. Solar dark matter searches provide complementary constraints to direct detection while probing spin-dependent dark matter interactions. Antimatter searches focus on detecting excess positrons, antiprotons, or antideuterons in cosmic rays that could result from dark matter annihilation. The Alpha Magnetic Spectrometer, AMSO2, on the International Space Station has measured cosmic ray, positron, and antiproton spectra with unprecedented precision, searching for spectral features that would indicate dark matter origins. Particle accelerator searches attempt to produce dark matter directly in high-energy collisions at facilities like the Large Hadron Collider, LHC. These experiments search for missing energy signatures when dark matter particles are produced but escape the detector without interacting, providing complementary information about dark matter properties and production mechanisms. The LHC experiments have searched for dark matter production in association with standard model particles like jets, photons, or Z-bosons that would provide detectable signatures for dark matter production events. These searches constrain models that connect dark matter to electroweak symmetry, breaking while probing dark matter masses accessible to collider energies. Quantum sensor technologies represent emerging approaches to dark matter detection that exploit quantum mechanics to achieve sensitivities beyond conventional detection methods. Atomic interferometry, precision atomic clocks, and superconducting quantum devices could detect dark matter interactions through their effects on quantum systems. Axion detection experiments use microwave cavities in strong magnetic fields to search for axion photon conversion, where axion dark matter would convert to detectable microwave photons with frequencies determined by axion mass. The Axion dark matter experiment at DMX has achieved sensitivity approaching the theoretical benchmark for axion dark matter in specific mass ranges. Alloscope experiments like at DMX scan through axion mass ranges by adjusting cavity resonant frequencies, searching for power excess that would indicate axion photon conversion. These experiments require superconducting magnets producing fields exceeding 8 Tesla and quantum-limited amplifiers to achieve necessary sensitivity levels. Network coordination between different detection approaches enables cross-checks and complementary information about dark matter properties. If one experiment claims a dark matter detection, other experiments using different techniques can test whether the signal is consistent with dark matter or results from unknown backgrounds or systematic effects. The global dark matter detection effort involves hundreds of scientists working on dozens of experiments across multiple continents, representing international collaboration on an unprecedented scale. This coordination ensures that detection claims can be independently verified while maximizing the scientific return from different experimental approaches. Data analysis challenges in dark matter experiments involve distinguishing extremely rare signals from much more common background events while maintaining rigorous statistical standards for discovery claims. Advanced machine learning techniques and sophisticated statistical methods are essential for extracting potential dark matter signals from complex datasets. Calibration systems ensure that detectors respond predictably to known particle interactions, enabling accurate interpretation of potential dark matter signals. Neutron sources, gamma-ray sources, and cosmic ray muons provide calibration data that validates detector performance and background models. The dream of dark matter detection drives continuous innovation in detector technology, background suppression, and data analysis while pushing the boundaries of what's experimentally possible. Whether dark matter is ultimately detected or ruled out, these experiments advance detector physics and precision measurement techniques, that benefit multiple scientific fields. Future detection concepts include space-based detectors that would avoid terrestrial backgrounds, novel target materials optimized for specific dark matter candidates, and revolutionary detection principles based on quantum technologies or entirely new physical phenomena. The ongoing search for dark matter represents humanity's most ambitious attempt to detect phenomena that interact almost exclusively through gravity while remaining invisible to every conventional detection method. These detection dreams embody both the technical sophistication of modern experimental physics and our determination to understand cosmic reality even when it hides from direct observation. Chapter 7. Underground Hunters Deep Beneath Earth's Surface. In laboratories carved from solid rock and shielded by miles of stone, some of the most sensitive scientific instruments ever constructed listen for whispers from the invisible universe. These underground dark matter detectors represent marvels of engineering and physics that must isolate microscopic signals from cosmic background noise while operating in pristine conditions, more sterile than surgical suites and quieter than the deepest ocean trenches. The Sanford Underground Research Facility, SURF, in South Dakota extends 4,850 feet beneath the Earth's surface in a former gold mine, providing natural shielding equivalent to 4,200 meters of water against cosmic radiation. This depth reduces the cosmic Raymond flux by a factor of nearly 2 million compared to surface conditions, creating an environment where subtle dark matter interactions might become detectable above background noise. Dr. Kevin Lesko, as leadership of underground laboratory development, has transformed abandoned mines into world-class research facilities, equipped with ultra-clean environments, vibration isolation systems, and electromagnetic shielding that exceeds the requirements of the most sensitive physics experiments. These laboratories represent unique resources that enable experiments impossible anywhere else on Earth. The Gran Sasso National Laboratory in Italy, located beneath 1,400 meters of rock in the Apennine Mountains, houses multiple dark matter experiments in halls large enough to accommodate detectors weighing hundreds of tons. The laboratory, as location beneath a major European highway, initially created vibration problems that required sophisticated isolation systems to achieve the mechanical stability needed for precision measurements. Underground detector construction requires extraordinary attention to material purity and contamination control. Every component that enters the detector volume must be screened for radioactive contamination at levels of parts per trillion or better. Stainless steel, copper, lead, and other construction materials undergo extensive purification and testing before they can be approved for use in dark matter detectors. The XENONNT experiment at Gran Sasso represents the current generation of liquid xenon dark matter detectors, containing 8.3 tons of ultra-pure liquid xenon maintained at -95 degrees Celsius in a stainless steel vessel surrounded by layers of shielding materials. The detector simultaneously measures scintillation light and ionization electrons produced when particles interact with xenon nuclei. Liquid xenon provides excellent properties for dark matter detection because it produces both light and electrical signals when particles deposit energy, enabling discrimination between nuclear recoils from dark matter and electron recoils from background radiation. Xenon's high atomic number enhances sensitivity to heavy dark matter particles, while its noble gas properties ensure chemical purity. The challenge of xenon purification requires removing trace contaminants that could absorb scintillation light or create radioactive backgrounds. Oxygen, water, and electronegative impurities must be reduced to concentrations below parts per billion through distillation, chemical getters, and continuous circulation through purification systems. Photomultiplier tubes surrounding the xenon volume detect scintillation light with single photon sensitivity, while electrode arrays measure ionization electrons that drift through the liquid under applied electric fields. The ratio of light to charge signals provides discrimination between different types of particle interactions based on their energy deposition mechanisms. The Lux-Zeppelin LZ experiment represents the next generation of liquid xenon detectors with 10 tons of active xenon mass and enhanced background rejection capabilities. LZ employs sophisticated pulse shape analysis, multiple veto systems, and improved radio purity to achieve sensitivity levels that could detect WIMP dark matter with cross-sections as low as 10 to 48 square centimeters. Cryogenic detectors operate at temperatures below 1 Kelvin to measure both phonon and ionization signals from particle interactions with semiconductor or superconductor targets. The Super-CDMS collaboration has developed silicon and germanium detectors that achieve excellent energy resolution and background discrimination through simultaneous measurement of multiple signal channels. Dr. Blas Cabrera's development of transition edge sensors enabled breakthrough sensitivity in cryogenic dark matter detectors by using superconducting films operated at their transition temperature, where small energy deposits create large changes in electrical resistance that can be measured with superconducting quantum interference devices, SQUIDs. The Edelweiss experiment in the Modane Underground Laboratory uses germanium bolometers operated at 20 millikelvin to detect nuclear recoils from dark matter interactions. These detectors achieve energy thresholds below 1 keV while maintaining excellent discrimination against electromagnetic backgrounds through measurement of both heat and ionization signals. Background sources in underground detectors include neutrons produced by cosmic ray muons interacting with surrounding rock, radioactive contamination from natural uranium and thorium decay chains, and radon gas that can emanate from construction materials or laboratory walls. Each source requires specific mitigation strategies and monitoring systems. Neutron backgrounds represent the most insidious problem for direct detection experiments because neutrons can scatter off nuclei and produce nuclear recoil signatures identical to those expected from dark matter. Neutron shielding using polyethylene, water, or other hydrogenous materials can moderate and absorb neutrons, but complete elimination requires active veto systems. The multiple scatter rejection technique exploits the fact that neutrons often interact multiple times within detector volumes, while dark matter particles would typically interact only once before escaping. Time-of-flight analysis can also distinguish neutron interactions that occur in sequence from single dark matter interactions. Radon mitigation requires sophisticated gas handling systems that continuously purge detector volumes with ultra-pure gases while monitoring radon concentrations at levels of microbecquerels per cubic meter. Radon daughters that played out on detector surfaces can create long-lived radioactive contamination that persists even after radon gas is removed. Active veto systems surround primary dark matter detectors with additional detector layers that identify cosmic ray muons and neutrons. When veto detectors register interactions, the primary detector data is excluded from dark matter searches to eliminate events that could result from cosmic ray interactions rather than dark matter. Liquid scintillator veto systems use organic liquids that produce light when particles deposit energy, enabling identification of muons and neutrons through their characteristic signatures. Water Cherenkov detectors exploit the fact that relativistic particles produce Cherenkov light in water, creating distinctive signatures for cosmic ray muons. The Cosine 100 experiment combines crystal scintillator technology with liquid scintillator veto systems to search for dark matter while testing claims from other experiments. This detector uses sodium iodide crystals similar to those used by the DAMA collaboration, which has reported annual modulation signatures that could indicate dark matter detection. Annual modulation searches exploit Earth's orbital motion around the Sun to look for seasonal variations in dark matter interaction rates that would result from Earth's changing velocity relative to the galactic dark matter halo. This technique could provide distinctive dark matter signatures, even with modest detector sensitivity. The Dama Libera experiment in Gran Sasso has reported statistically significant annual modulation in their sodium iodide detectors for more than 20 years. But other experiments using different target materials have not confirmed this signal. Understanding this discrepancy remains one of the major controversies in dark matter physics. Underground laboratory expansion includes new facilities under construction in multiple countries to house next-generation dark matter experiments. There's no lab facility in Canada, the China Jinping Underground Laboratory, and proposed facilities in Australia and elsewhere will provide additional underground research capacity. The Deep Underground Neutrino Experiment, DUNE at SURF, will share the laboratory with dark matter experiments, creating synergies between different physics programs while requiring careful coordination to minimize interference between experiments with different operational requirements. Future underground detectors will incorporate advanced technologies, including improved photosensors, novel target materials, and enhanced background rejection techniques. The Darwin collaboration plans to build a 50-ton liquid xenon detector that could definitively test WIMP dark matter across the entire theoretically motivated parameter space. Directional detection underground requires low-pressure gas detectors that can track the paths of recoiling nuclei to measure both energy and direction of dark matter interactions. These experiments face additional technical challenges but could provide unambiguous dark matter signatures through detection of the expected directional anisotropy. The Underground Dark Matter Hunting Program represents a remarkable international collaboration involving thousands of scientists working in facilities that required billions of dollars in construction and infrastructure development. These experiments push detector technology to theoretical limits while searching for phenomena that might not exist or might interact too weakly to detect with current methods. Underground hunters continue their patient vigil in the depths of the Earth, listening for signals from invisible particles that could revolutionize our understanding of cosmic reality. Whether they succeed in detecting dark matter or ultimately prove that it interacts too weakly to observe, these experiments represent humanity's most determined effort to illuminate the cosmic darkness that surrounds us. The underground laboratories and their sensitive detectors embody both the technical sophistication of modern experimental physics and our determination to answer fundamental questions about cosmic reality, even when that reality hides from every conventional detection method we can devise. Chapter 8. Alternative theories. While most astronomers and physicists accept dark matter as the explanation for anomalous gravitational effects throughout the universe, a persistent group of theorists has proposed that these phenomena might result from modifications to gravity itself rather than invisible matter. These alternative theories suggest that Einstein's general relativity, despite its remarkable successes, might break down on cosmic scales, requiring fundamental revisions to our understanding of spacetime and gravitational physics that eliminate the need for dark matter entirely. Modified Newtonian dynamics, MOND, proposed by Mordechai Milgram in 1983, represents the most developed alternative to dark matter and has achieved remarkable success in explaining galactic rotation curves and other gravitational anomalies without invoking invisible matter. Mont proposes that Newton's second law of motion breaks down when accelerations fall below a critical threshold, approximately 10 to 10 meters per second squared, with profound implications for gravitational physics on cosmic scales. Milgram's original motivation for Mont came from recognizing that the anomalous accelerations in galaxy rotation curves all occur in the regime where gravitational accelerations approach a characteristic scale related to cosmic expansion. This coincidence suggested that gravity itself might behave differently at very low accelerations rather than requiring enormous amounts of invisible matter to explain observed phenomena. The Mond acceleration scale is 0 approximately equals 1.2 times 1010 meters per second squared appears throughout astronomical observations as the characteristic acceleration where gravitational anomalies become apparent. This scale relates to fundamental cosmological parameters, including the Hubble constant and cosmological constant, suggesting deep connections between local gravitational physics and global cosmic properties. In the Mond framework, Newton's second law F equals ma becomes modified when accelerations fall below a zero, with the effective gravitational force enhanced compared to Newtonian predictions. This modification naturally explains flat galaxy rotation curves without requiring dark matter halos, while preserving standard Newtonian physics in high acceleration regimes where it has been thoroughly tested. Dr. Stacy McGaw's extensive analysis of galaxy rotation curves demonstrates that Mond predictions match observational data with remarkable precision across 4 orders of magnitude in galaxy mass and size. The theory successfully predicts rotation curve shapes, velocity dispersions, and dynamical properties of galaxies using only their visible matter distributions and the single parameter as 0. The Tully-Fisher relation, which relates galaxy rotation velocity to luminosity, emerges naturally from Mond as a consequence of the modified dynamics, whereas dark matter models struggle to explain why this relation should be so tight and fundamental. Mond predicts the exact form and normalization of the Tully-Fisher relation without additional assumptions or fine-tuning. However, extending Mond to a fully relativistic theory that can address cosmological observations has proven challenging. Several relativistic generalizations of Mond have been proposed, including tensor vector scalar, TeVs, gravity by Jacob Bekenstein. But these theories face difficulties in simultaneously explaining galactic dynamics and cosmological observations. The most serious challenge for Mond comes from observations of galaxy clusters, particularly the bullet cluster collision, where gravitational lensing reveals mass distributions displaced from visible matter in ways that seem to require dark matter. Mond proponents argue that cluster dynamics might involve additional physics beyond simple point masses, but these explanations remain less compelling than for galactic systems. Cosmological observations present additional challenges for Mond theories because the cosmic microwave background, Big Bang nucleosynthesis, and large-scale structure formation all seem to require dark matter in addition to modified gravity. Some Mond variants include sterile neutrinos or other exotic matter to address these cosmological requirements. Emergent gravity theories propose that gravitational physics emerges from more fundamental microscopic physics in ways that could naturally explain dark matter phenomena. Eric Volein's entropic gravity suggests that gravity results from thermodynamic properties of spacetime, with dark matter effects emerging from modifications to gravitational physics rather than additional matter. Volein's theory relates gravitational acceleration to entropy gradients and information storage on holographic surfaces, predicting modifications to gravitational physics that mimic dark matter effects. While intriguing, these ideas remain highly speculative and face significant challenges in making precise predictions that can be tested observationally. Extra-dimensional theories suggest that gravity might be modified by the presence of additional spatial dimensions beyond the 3 we experience directly. Large extra dimensions could allow gravity to leak into higher dimensional space, weakening gravitational effects in ways that might require dark matter to compensate for apparently missing gravitational attraction. Vali-Gabadadze-Parati, DGP. Gravity proposes that our 4-dimensional spacetime is a membrane embedded in 5-dimensional space, with gravity following 4-dimensional physics at short distances, but 5-dimensional physics at large scales. This crossover could modify gravitational dynamics on cosmic scales in ways that affect galaxy and cluster dynamics. FR gravity theories modify Einstein's equations by replacing the Ricci scalar r with functions fr that could produce different gravitational behavior at different scales or curvatures. These theories can potentially explain cosmic acceleration without dark energy while modifying gravitational dynamics in ways that affect dark matter observations. Chameleon field theories propose scalar fields that couple to matter and change their effective mass depending on local matter density. In high-density regions like the solar system, chameleon fields become heavy and decouple from matter, preserving standard gravitational physics. In low-density cosmic environments, they become light and create long-range forces that could mimic dark matter effects. Modified theories must pass stringent tests from solar system observations, where general relativity has been confirmed with extraordinary precision. Parameterized post-Newtonian tests, lunar laser ranging, and gravitational wave observations all constrain possible modifications to gravitational physics on scales where Einstein's theory has been thoroughly validated. The Lense-Thirring effect, gravitational redshift, time dilation, and perihelion precession all agree with general relativity predictions to high precision, limiting possible modifications to gravity that could explain dark matter phenomena. Any viable alternative theory must reproduce general relativity in well-tested regimes while producing significant modifications only in untested cosmic environments. Observational tests of alternative gravity theories focus on finding distinctive predictions that differ from dark matter scenarios. Galaxy-galaxy weak lensing, cluster dynamics, and cosmic structure formation provide tests where modified gravity and dark matter make different predictions that can potentially be distinguished observationally. The cosmic microwave background provides particularly stringent constraints on modified gravity theories because the acoustic oscillation patterns depend sensitively on gravitational physics during cosmic recombination. Most alternative theories struggle to reproduce observed acoustic peak positions and amplitudes without invoking additional dark matter components. Gravitational wave astronomy offers new tests of gravitational physics that could constrain or confirm modifications to general relativity. The propagation speed of gravitational waves, their polarization properties, and their production mechanisms in strong gravitational fields all provide tests of alternative gravity theories under extreme conditions. Binary pulsar timing measurements provide precision tests of gravitational physics in strong field regimes, where some alternative theories might produce detectable deviations from general relativity. The remarkable agreement between pulsar timing observations and general relativity predictions constrains possible modifications to gravitational physics. Computer simulations of cosmic structure formation using modified gravity theories reveal whether alternative theories can explain observed cosmic structure without dark matter. These simulations face computational challenges because modified gravity often involves nonlinear field equations that are difficult to solve numerically. The debate between dark matter and modified gravity represents a fundamental question about the nature of gravitational physics and cosmic reality. Dark matter preserves general relativity by introducing new matter components, while modified gravity preserves the matter content of the universe by revising gravitational physics itself. Future observations, including improved measurements of cosmic structure, gravitational lensing, and cosmic expansion, will provide increasingly stringent tests of both dark matter and modified gravity scenarios. Large-scale survey experiments like the Large Synoptic Survey Telescope will measure millions of galaxy properties with unprecedented precision. The Euclid Space Mission and other surveys will map cosmic structure and gravitational lensing with sufficient precision to distinguish between dark matter and modified gravity through their different predictions for structure formation and cosmic expansion history. Alternative theories remind us that scientific progress sometimes requires questioning fundamental assumptions about physical reality. Whether dark matter exists or gravity requires modification, Resolving this question will deepen our understanding of cosmic physics while potentially revolutionizing our comprehension of space-time, matter, and cosmic evolution. The persistence and sophistication of alternative gravity theories demonstrates that the dark matter question touches on fundamental issues about the nature of gravitational physics that remain unresolved despite decades of theoretical and observational progress. Understanding cosmic reality might require either discovering new forms of matter or revising our understanding of spacetime itself. Chapter 9. Cosmic Architecture. Dark matter serves as the invisible architect of cosmic structure, providing the gravitational scaffolding upon which everything visible in the universe is built. From the largest superclusters of galaxies to the smallest dwarf galaxies, dark matter's gravitational influence shapes cosmic architecture on scales spanning 12 orders of magnitude, creating the framework that enables stars to form, galaxies to evolve, and complex structure to emerge from the nearly uniform conditions present shortly after the Big Bang. Computer simulations of cosmic evolution reveal that without dark matter, the universe would be a vastly different and far less interesting place. The illustrious and Eagle simulations, which follow cosmic structure formation from early dark matter fluctuations to present-day galaxy populations, demonstrate that dark matter halos provide essential gravitational wells where ordinary matter can collect, cool, and eventually form stars and galaxies. The cosmic web represents dark matter architecture's grandest expression, consisting of filaments, nodes, and vast voids that span billions of light years. Dr. Dupshay and the Eagle collaboration have shown how dark matter halos merge hierarchically over cosmic time, creating increasingly massive structures while maintaining characteristic density profiles that reflect the gravitational physics governing structure formation. Dark matter halos exhibit universal properties that emerge from gravitational collapse dynamics, regardless of halo mass or formation history. The Navarro-Frank-White NFW profile describes how dark matter density varies with radius in gravitationally collapsed structures, showing characteristic cuspy central profiles that steepen toward galactic centers while extending to large radii where density falls off as R to 3. Dr. Julio Navarro's analysis of cosmological simulations revealed that dark matter halos spanning 8 orders of magnitude in mass all exhibit similar density profiles when properly scaled, suggesting universal physics governing gravitational collapse. This universality implies fundamental relationships between dark matter, properties and structure formation that constrain dark matter's nature. Galaxy formation within dark matter halos involves complex feedback processes between dark matter gravity, gas dynamics, stellar evolution, and supermassive black hole growth. The interplay between these processes determines galaxy properties including stellar masses, star formation rates, morphologies, and chemical abundances, while creating the observed diversity of galaxy types. The abundance matching technique relates observed galaxy properties to dark matter halo masses by connecting galaxy stellar mass functions with theoretical halo mass functions from cosmological simulations. Dr. Risa Wexler and others have shown that this relationship reveals how efficiently dark matter halos convert gas into stars across different mass scales and cosmic epochs. Dwarf galaxies provide crucial tests of dark matter's role in cosmic architecture because they represent the smallest scale on which dark matter halos can retain gas and form stars. The local group contains dozens of dwarf satellite galaxies whose properties encode information about dark matter physics, reionization history, and feedback processes during early cosmic evolution. The missing satellite problem highlights discrepancies between predicted numbers of dark matter subhalos and observed satellite galaxies around the Milky Way and Andromeda. High-resolution simulations predict hundreds of dark matter subhalos massive enough to host galaxies, while only a few dozen satellite galaxies are observed. suggesting that most small dark matter halos remain dark. Reionization feedback from the first stars and quasars can suppress star formation in small dark matter halos by heating and ionizing cosmic gas, preventing it from cooling and forming stars. Dr. Quinn et al. Have shown that photoionization feedback naturally explains the missing satellite problem by creating a minimum dark matter halo mass required for galaxy formation. The Corcus problem represents another challenge for standard dark matter models, as observations suggest that many dwarf and low-surface brightness galaxies have flat central density profiles rather than the cuspy profiles predicted by gravitational collapse simulations. This discrepancy might indicate dark matter self-interactions, baryonic feedback effects, or alternative dark matter physics. Supernova feedback and stellar winds from massive stars can modify central dark matter distributions by creating time-varying gravitational potentials that transfer energy to dark matter particles. Dr. Ponson and Gavinato have demonstrated that repeated gas outflows can flatten central dark matter cusps in low-mass galaxies while preserving cuspy profiles in more massive systems. Strong gravitational lensing by galaxy clusters provides direct maps of dark matter distributions through measurements of how background galaxy images are distorted by foreground mass concentrations. These observations reveal that dark matter distributions often differ from visible galaxy distributions, confirming dark matter's existence while constraining its clustering properties. The Hubble Space Telescope's observations of strong lensing systems have revealed dark matter substructure within galaxy clusters through perturbations to lensed image positions and flux ratios. These substructure detections provide direct evidence for dark matter clumping on scales from individual galaxies to entire clusters. Weak gravitational lensing surveys, like the Kilodegree Survey and Dark Energy Survey, measure statistical correlations in galaxy shape distortions to map dark matter distributions across cosmic scales. These observations reveal how dark matter clustering evolves with cosmic time while providing precision tests of cosmological structure formation models. The cosmic shear signal measured by weak lensing depends on both dark matter clustering strength and cosmic geometry, enabling simultaneous constraints on dark matter properties and dark energy evolution. Current measurements show good agreement with predictions from the standard CDM cosmological model while reaching precision levels that test alternative cosmological scenarios. Galaxy cluster formation represents the largest scale where dark matter architecture can be directly observed through X-ray emission from hot intracluster gas and gravitational lensing from total cluster mass. The most massive clusters contain dark matter halos with masses exceeding YP solar masses and extend over volumes spanning several megaparsecs. The intracluster medium provides a tracer of gravitational potential wells created by dark matter concentrations, while also demonstrating how baryonic physics modifies dark matter distributions through feedback from active galactic nuclei, stellar evolution, and gas dynamics. These processes create complex relationships between dark and visible matter. Cluster mergers, like the Bullet cluster, provide natural experiments that separate dark matter from ordinary matter through differential responses to collision dynamics. Dark matter passes through collisions nearly unaffected, while ordinary matter experiences friction and heating that modifies its distribution, creating spatial offsets that prove dark matter's existence. Dark matter's role in cosmic architecture extends to determining when and where the first stars and galaxies formed through its control of gravitational collapse timescales and cooling rates. The first stars formed within dark matter mini-hollows with masses around YY solar masses when the universe was approximately 100 to 200 million years old. Population 3 star formation within primordial dark matter halos required gas cooling through molecular hydrogen since heavier elements hadn't yet been synthesized. The efficiency of this cooling process depended on dark matter halo properties including mass assembly history, concentration, and local environment within the cosmic web. Supermassive black hole formation and growth depends on dark matter architecture through the merger histories of galaxy hosting, halos, and the gas accretion processes that feed central black holes. The correlations between black hole masses and galaxy properties likely reflect underlying relationships with dark matter halo masses and merger histories. Active galactic nuclei feedback affects cosmic architecture by heating gas within dark matter halos and potentially suppressing star formation and cooling flows in massive clusters. This feedback couples supermassive black hole growth to dark matter halo properties while modifying baryon distributions within dark matter structures. The local group's architecture reflects dark matter physics through the orbital dynamics of the Milky Way and Andromeda galaxies, their satellite populations, and the overall mass distribution within the local group volume. Measurements of local group dynamics provide constraints on dark matter properties and cosmological parameters. Future surveys will map cosmic architecture with unprecedented detail through gravitational lensing measurements, redshift surveys, and multi-wavelength observations that reveal relationships between dark matter, gas, and stellar components across cosmic time. The Large Synoptic Survey Telescope will observe billions of galaxies to trace cosmic structure evolution. Understanding cosmic architecture requires integrating observations of dark matter clustering, galaxy formation physics, and cosmic expansion history while accounting for complex feedback processes that couple dark matter gravity to baryonic physics. This integration tests our understanding of cosmic evolution while constraining dark matter properties. The Euclid space mission will map cosmic structure and gravitational lensing with precision sufficient to constrain dark matter clustering properties, test alternative gravity theories, and measure cosmic expansion history. These observations will provide new tests of dark matter's architectural role in cosmic evolution. Dark matter's role as cosmic architect reveals deep connections between invisible matter physics and visible cosmic structure that span scales from dwarf galaxies to superclusters. Understanding these connections provides insights into both dark matter properties and cosmic evolution while demonstrating how invisible physics shapes visible reality. The cosmic architecture built by dark matter creates the framework that enables complexity, structure, and ultimately life to emerge from simple initial conditions through gravitational instability and cosmic evolution. This architecture reveals that cosmic reality depends fundamentally on invisible matter that outweighs everything we can see by more than 5 to 1. Chapter 10. Quantum Mysteries. The mystery of dark matter extends far beyond astrophysics into the deepest foundations of quantum mechanics, particle physics, and our understanding of reality itself. Dark matter's properties challenge fundamental assumptions about matter, observation, and existence while potentially connecting cosmic evolution to quantum field theory, extra dimensions, and physics beyond the standard model that could revolutionize our comprehension of what matter is and how reality operates at its most basic level. Quantum field theory provides the theoretical framework for understanding how dark matter particles could exist while remaining invisible to electromagnetic radiation and ordinary matter interactions. In quantum field theory, particles represent excitations of underlying fields that permeate all space, with different fields corresponding to different types of particles and forces that determine how particles interact with each other. The standard model of particle physics describes 3 of the 4 fundamental forces through quantum field theory, but it contains no candidates for dark matter particles, suggesting that dark matter requires extensions to our current understanding of fundamental physics. These extensions could involve supersymmetry, extra dimensions, additional gauge symmetries, or entirely new types of quantum fields. Supersymmetry represents the most extensively studied extension to the Standard Model that naturally provides dark matter candidates through the prediction that every known particle has a superpartner with different spin statistics. The lightest supersymmetric particle would be stable due to ray parity conservation and could serve as dark matter while solving other problems in particle physics, including the hierarchy problem. Dr. Michael Dine's work on supersymmetry breaking mechanisms shows how supersymmetric particles could acquire masses while preserving the stability of the lightest supersymmetric particle. Different supersymmetry breaking scenarios predict different dark matter properties and detection signatures, creating a rich phenomenology for experimental tests. Extra-dimensional theories propose that dark matter particles might propagate through spatial dimensions beyond the three we experience directly, making them invisible to ordinary matter confined to our three-dimensional brain, while allowing gravitational interactions that affect cosmic structure formation. These theories connect dark matter to fundamental questions about spacetime dimensionality. String theory naturally incorporates extra dimensions and predicts numerous additional particles that could serve as dark matter candidates, including axions from string compactification, Kaluza-Klein excitations of Standard Model particles, and exotic particles unique to string theory frameworks. The landscape of string theory vacua provides enormous variety in possible dark matter physics. Quantum chromodynamics, the theory describing strong nuclear interactions, contains its own dark matter candidate in the form of axions that emerge from solutions to the strong CP problem. The axion field represents a novel type of quantum field that could fill the universe while interacting only weakly with ordinary matter through electromagnetic field mixing. The QCD axion mass depends on the scale of Peck-Equin symmetry breaking and could range from y-6 to 10 to 3 electron volts, making axions extraordinarily light particles whose quantum properties become important on astrophysical scales. These quantum effects could modify cosmic structure formation and galactic dynamics in observable ways. Quantum vacuum fluctuations provide another connection between dark matter and fundamental quantum physics through the possibility that dark matter consists of modifications to quantum vacuum energy density rather than traditional particles. These scenarios involve vacuum phase transitions, false vacuum decay, or novel quantum field configurations. The Kazan-logical constant problem reveals deep mysteries about quantum vacuum energy that might relate to dark matter physics. Quantum field theory predicts vacuum energy densities vastly larger than observed, while observations suggest that vacuum energy contributes to cosmic acceleration. Understanding this discrepancy might illuminate dark matter's nature. Quantum entanglement between dark matter particles could create non-local correlations that affect dark matter clustering and interaction, properties in ways that differ from classical particle behavior. These quantum correlations might leave observational signatures in cosmic structure formation or dark matter detection experiments. Dark matter might exist in quantum superposition states that enable it to simultaneously occupy multiple spatial locations or energy states, creating quantum interference effects that modify gravitational interactions or detection probabilities. These quantum mechanical properties could explain dark matter's elusive nature while suggesting new detection strategies. Measurement and decoherence effects could play crucial roles in dark matter physics if dark matter particles exist in quantum superposition, states that collapse only during specific types of interactions. The quantum measurement problem might extend to dark matter in ways that affect its observational properties and interaction rates. Quantum tunneling could enable dark matter particles to escape from gravitational potential wells or penetrate potential barriers in ways that affect structure formation, detection experiments, or particle production mechanisms. These quantum mechanical effects become important when dark matter de Broglie wavelengths approach macroscopic scales. The uncertainty principle places fundamental limits on simultaneously measuring dark matter particle position and momentum, creating quantum constraints on dark matter detection experiments and astronomical observations. These limits might explain why dark matter remains so elusive while suggesting optimal detection strategies. Quantum spin properties of dark matter particles determine their statistics and interaction symmetries in ways that affect everything from primordial production mechanisms to detection cross-sections to clustering properties in cosmic structure formation. Fermionic dark matter follows Pauli exclusion statistics, while bosonic dark matter can form Bose-Einstein condensates. Composite dark matter scenarios propose that dark matter consists of bound states formed through dark sector forces analogous to quantum chromodynamics, creating dark hadrons, dark nuclei, and potentially dark atoms with rich internal structure and quantum mechanical properties that affect their cosmic behavior. Quantum phase transitions in dark matter could occur during cosmic evolution as dark matter densities and temperatures change, potentially affecting dark matter clustering properties, interaction rates, and observational signatures. These phase transitions might connect dark matter physics to condensed matter physics and many-body quantum systems. Dark matter quantum numbers, including charge, baryon number, lepton number, and hypothetical dark charges, determine conservation laws that affect particle interactions, stability, and production mechanisms. Understanding these quantum numbers could provide insights into dark matter's fundamental nature and cosmic role. Quantum field theoretic calculations of dark matter production in the early universe involve sophisticated techniques including thermal field theory, out-of-equilibrium dynamics, and quantum statistical mechanics that determine dark matter abundance, velocity distributions, and clustering properties during cosmic evolution. Symmetry breaking mechanisms that give mass to dark matter particles while preserving their stability represent deep connections between dark matter, physics, and fundamental symmetries of nature, including gauge symmetries, global symmetries, and potentially new symmetries beyond the standard model. The CP violation and matter-antimatter asymmetry that created ordinary matter abundance might also affect dark matter through shared mechanisms that produce both dark and visible matter asymmetries during cosmic evolution. These connections could explain observed ratios between dark and ordinary matter densities. Quantum gravity effects might become important for dark matter physics if dark matter particles approach Planck scale masses or interact through gravitational mechanisms that probe quantum spacetime structure. These effects could connect dark matter to theories of quantum gravity and emergent spacetime. Holographic principles suggest that dark matter information might be encoded on cosmic boundaries rather than distributed through three-dimensional space, connecting dark matter to fundamental questions about information theory, quantum gravity, and the relationship between geometry and quantum mechanics. Quantum information theory provides frameworks for understanding how dark matter particles could process and store information while remaining largely invisible to ordinary matter. These information theoretic approaches might reveal new aspects of dark matter physics and its role in cosmic evolution. The quantum mechanics of dark matter detection experiments involves understanding how quantum measurements affect particle interactions, how quantum noise limits detector sensitivity, and how quantum correlations might enhance detection strategies through entanglement-based sensors or quantum-enhanced detection protocols. Future developments in quantum technology, including quantum sensors, quantum computers, and quantum communication, might enable new approaches to dark matter detection that exploit quantum mechanical effects to achieve sensitivities beyond classical limits or probe dark matter properties through quantum interactions. Understanding dark matter's quantum mysteries requires integrating particle physics, cosmology, and quantum mechanics while confronting fundamental questions about measurement, reality, and the relationship between quantum mechanics and gravitational physics. These investigations push the boundaries of both theoretical and experimental physics. The quantum nature of dark matter connects cosmic evolution to fundamental physics in ways that could revolutionize our understanding of matter, space-time, and reality itself. Whether dark matter consists of known quantum particles, exotic quantum fields, or entirely new types of quantum mechanical entities, its discovery would illuminate deep connections between cosmic structure and quantum physics. These quantum mysteries reveal that dark matter represents more than an astronomical curiosity. It's a probe into fundamental physics that could unlock new understanding about quantum mechanics, particle physics, and the quantum foundations of cosmic reality that enable complexity and consciousness to emerge from quantum vacuum fluctuations.